In today's class, we will solve how to evaluate basic AC circuit analysis in frequency domain and how to find their equivalent circuits using different laws we had studied for using the DC analysis. We will solve different same kind of circuits, however, we're going to find their equivalent circuits in frequency domains. And before that, we should really know all the key um, theorems and laws. For example, Kirchhoff's current law, Kirchhoff's voltage law, current and voltage division rules, circuit analysis techniques, for example, nodal, mesh, loop, superposition, source transformations, etc. Right? So I start with the basic this circuit, which is already given in frequency domain, right? Because your voltage is given in phasor. The phasor representation of voltage is given as Vs. You have a resistor, two resistors, inductor. The impedance for the inductors is already given, J6, and impedance of a capacitor is already given to you. So what you are being asked is to find out V1, right? Find out V1. So in order to find V1, so V1, as you can see, is nothing here, but V1 is equal to the source. The AC component of V1 is the source voltage minus 4 times I1 current, right? So this is what we need to find out. So for in this case, we need to find out I1. I1 is the current which is flowing here, right? So we need to find out I1, which is nothing but the source voltage divided by the equivalent impedance for this whole circuit by looking from here, right? So which means that we need to find out what is the equivalent impedance for this whole network. To do so, we will write the equation. We know that these two 8 ohms and the capacitor are in series with each other, and they both are in parallel with the inductor. And then this is in series with the resistor, 4 ohms. So we have to write this in the form of equation, and we will write this as 4 plus, so 4 ohm is in series with a parallel combination of inductor and resistor and a capacitor, divided by J6 plus 8 minus J4. Right, so this is a series combination. This is a series combination. This series combination is in parallel with the inductor. This equivalent of this will be in series with 4 ohm. This is exactly what I wrote here in this equation. I will solve this one, and this can be written as J48 divided by 8 plus J square, right? And we know that J squared is minus 1. So when we solve this one, we get 4 plus 4.24 plus J 44.94, this is in rectangular representation, so which will be in phasor representation as given here. Oops. Yeah. So again, I repeat, when you will have an answer of this one in the form of x and y coordinates, the phasor representation 9.6 might come as, this is V peak as x squared plus y squared, and theta value comes from tan inverse of y over x, right? So we got the value for the equivalent impedance. Now we need to find out, put this value in equation number 2 to find out the current I1, which is going to be Vs over the equivalent impedance, which is 24 angle 60, divided by this value, which is equal to 2.5 angle 29.06. amperes. This is current, right? And we put this value of I1 into this V1, equation number 1, and we find out V1 as Vs, which is 24 angle 60 minus 4 times I1, right? Minus 4 times I1, which is 2.5 angle 29.06, which is equal to this value, volts. So now we have V1, we can actually find out all the rest of the components. We can find V2, we can find I1, we already have I1, we can find I3 as well, right? So we can find each and every single component, current paths and voltages across each and every circuit element for this circuit, right? So similarly, if a circuit is not given in frequency domain, and it is given in time domain, the voltages are given in time domain, and only the capacitor or resistor value is given to you, how you can solve it. This is the voltage source. Let's say its value is 20 cosine of 40, right? So omega is 4, and we have 20 as an amplitude. We have a resistor connected. Let me draw the circuit. These are the values for inductors. There are 2 inductors. This is the capacitor, 0.1 farad. This is Ix. We need to find Ix in this circuit. And this is the dependent current source, which is dependent upon this Ix. Right? So this is Ix, so 2Ix. So we need to find this Ix. Okay. So this first step, let me change the color. So the first step is convert the circuit to its frequency domain, right? So it will make things simpler for us and easier to solve. So the first thing is I need to change this source to its phasor representation. So this is 20 cos of 40, and the theta is 0 for this one. So this can be simply written as 20 angle of 0, right? And what is its omega? It is 4 radians per second. So angular frequency is 4 radians per second. The first resistor is 10 ohm. So capacitor. So the capacitor, 0.1 farad. You can convert that to from 1 over j omega c, which is going to be 1 over j is minus j, and we already know why is that, because this is 1 over j, which is equal to 1 over j times j over j, which is equal to j over j squared. J squared is minus 1, so this is going to be minus j. Okay, so this is going to be minus j 2.5 on calculating. So the 1 Henry inductance can be replaced by its equivalent impedance as the j omega L, which is going to be j 4, omega is 4. And the last inductance 0.58 Henry is also j omega L, which is omega is 4, 2, so it is 2 of j or j2. Right, so 10 ohm resistor will remain the same as 10 ohms in frequency domain. So I will redraw this circuit in frequency domain now, and I will write these components the same way as I just calculated. So these are all the components. So I will not do anything on this current source because this is a dependent source which is dependent upon this IX. This IX or IX, you should use the same notation, although it's a AC current. So I will better represent it like this one. So, okay. So now let me write these values: J 2.5, J2, J4. Perfect. Okay. So in this analysis, the first thing I should do is I should label the voltages at each nodes, and I should label the current as well. So we have these nodes V1, and we have another node V2, right? So let's say I label this current as here. This is already IX, and this current is flowing here. We already know the direction for this current, and we'll just keep it the same for simplicity. And this is this direction. All right, so we label all the current directions and we label the voltages at two nodes, V1 and V2. We will apply the Kirchhoff's current law, Kirchhoff's current law, KCL, at node 1 and node 2. So at node 1, the KCL is going to be, so what is the value of this one? This is 10 ohms. So 20 minus V1 divided by 10. So this 20 minus V1 divided by 10. So the current, remember the Kirchhoff's law, the current entering equals to current leaving. So current entering node 1 is only this current, and rest of them are leaving currents. So this leaving current is going to be V1 over negative J2.5 plus V1 minus V2 divided by the inductor J4. So this is our first equation at node 1. Similarly, we can write KCL at node 2 as, what is node 2? So we have a current entering, which is a dependent current source 2IX, and there is another current entering, which is coming from the inductor J4. So we will write that as the current is, so remember the current is entering from V1 to V2. So we will start it from V1 minus V2 divided by J4 equals to current leaving, which is V2 divided by J2. This is our second equation, right? We can also write IX, which is a dependent source. IX can also, oh, 1 second. Okay, so we can also write IX oops, yeah. All right, so yeah, I'll stop the recording here because my pencil is out of charge. So IX, which is a dependent current source, can be written as, since this is the current flowing through this V1 node to ground, so this is our reference point. So V1 divided by minus J.25. So when we calculate this one, we can write this IX as, after calculating these 1 and 2 simultaneous equations, we will find V1 and we'll put this value in this third equation, and we can find out IX as this. So again, we can transform this one into time domain as well. So after we transform this one in time domain, because our first representation of the source voltage was in time domain, so we can also write this Ix as 7.59 cos of 40. 40 is the angular frequency plus the phase. All right. So this is how we can solve any circuit using similar technique. So let's say we have this circuit and we need to find out I naught. So we need to find out I naught in the circuit, and this is using the nodal analysis. We studied nodal analysis for the DC analysis when we did. Now this is using the frequency domain. We need to find out I naught using nodal analysis. So find out I naught, which is here. And simply you need to, the first thing you need to identify is that you have a supernode here. So the voltages are given to you and you have a supernode here between two voltages, V1 and V2, right? So we can simply write, the first thing you need to identify is find out what are the directions of the current, or label the directions of current, right? So you can label any direction of current you want. So let's say I labeled the currents in these direction as this direction and this direction. Now we will write the loop equation as, we will apply Kirchhoff's current law to the supernode, and we will have just one equation, one loop equation, because we have a supernode, which makes, I believe, things more easier. And we will write the loop equation as V1 divided by the series combination of 1 resistor and J1 inductor, 1 plus J1. Now this current is actually opposite direction to the label direction, so we will write this as -2 angle 0. And now this is a super node, so we will switch to V2 node and write the currents, which both are going outside the outward from the V2. So we will write this as plus V2 over 1 ohms plus V2 divided by 1 minus J. So again, I just put these two in series combination. So V2 divided by 1 minus J equals to 0. So this is our first equation. And whenever you have a supernode, you need to write a supernode equation. So in this case, the supernode equation is V1 minus V2 equals to this, right? So this is our supernode equation. So again, we have two simultaneous equations. We can solve simply two simultaneous equations to find out what is V1 and what is V2. And when you solve this one, you will get to this answer, which I'm directly putting here for you to solve and verify. And now what is our goal? We need to find out I naught. Where is I naught? I naught is simply V2 divided by 1 ohm. I naught is simply here, V2 divided by 1 in this branch. So I naught equals to V2 divided by 1 ohm, which is equal to 2.91 amperes. So again, if you know how to find out the impedances for the circuit in frequency domain, you should be able to solve this pretty easily if you have a firm understanding of from the DC analysis, circuit analysis, right? And we studied many different analysis, nodal analysis, loop analysis, mesh analysis, and different theorems. All right, so this is another circuit, and you need to, and already the loops are given to you. So you have to use loop analysis, and you need to find out what you need to find out. You need to find out I naught in the circuit. So find out I naught, and already loop current directions are given to you, right? So you can either choose these directions. So it's already given to you. So I will just use the same directions. So the first thing I know is the I1 is nothing but, so the direction for I1 is in opposite direction to this already current source which is given to me. So I already know the value of I1, which is -2, right? Now I will follow this loop, this outward loop, to write out the loop equation, which is going to be 1. So I1 is flowing through this one, and I2 are. So both I1 and I2 are flowing in the same direction from in this 1 ohm resistor. So I will write as I1 plus I2. In J1, we have I1 flowing, and we also have I2 flowing, right? So this is I2, this is I1, and this is I3. So in J1, this is J1, we have again two currents flowing, which is I1 and I2. Then we have a voltage source. And remember, this voltage source is connected, negative terminal is first and positive terminal is second. So we will write -6, plus in 1 ohm, we have again two currents flowing. Now it is I2 and I3, and both of them are flowing in the same direction. So we will simply write I2 plus I3. And then we have a capacitor, -J1, I2 plus I3 equals to 0. This is my second loop equation. I have the third loop, which is I3. And I can write the loop equation for I3, which is this last loop, I3, as 1 times, so this 1 ohm has only I3 flowing in it. So 1 time I3 plus this, the above 1 ohm, the top 1 ohm has two currents flowing, I3 and I2. So I3 plus I2 minus J1, again I2 plus I3 equals to 0. So this is my third loop equation. So I have two unknowns now, I2 and I3. I already know I1, which is given to me. So again, I can simply solve these two simultaneous equations and find out I2 and I3. I2, I have calculated to be this, and I3, I have calculated to be this value in frequency domain. Now, what was our goal? We need to find out I naught. What is I naught here? I naught is flowing through this 1 ohm resistor. And what did we label them? We label them as I3. However, the I3 direction is opposite to I naught direction, right? So we will call this I naught equals to negative I3, right? This is negative I3. And this is how this is going to be this value. Okay. So please remember that I naught, when it is negative I3, which means that you have to flip its phase. And what does that mean? Is that the magnitude is the same. However, it is now, you have to subtract 180 degrees to make it. Now this is going to be, this is now I naught, right? So let's say, what does this mean? If you have this amplitude, right, this magnitude, the inverse or complete opposite for negative A is going to be here. Is going to be here. So this is how you are basically changing only the phase. However, the magnitude will remain the same. So this is again very important to remember, right? All right, so let's move forward and solve, solve the superposition. So if you remember what was superposition when we studied DC analysis was, in a superposition, again, what you need to do is that you need to find out whatever is asked for you to find out. For example, in this case, you need to find I naught. In superposition, you have to keep only one source at one time. So this is the rule for this one. Keep only one source and remove the other sources. What does removing the other sources means? If you keep only the, in this circuit, for example, you have two sources. You have a current source and you have a voltage source, right? So let's say I want to keep only the current source in the first case. So keep only current source. When I keep only current source, what I will do with the voltage source here is that I will short circuit the voltage source. Short circuit voltage source, right? So I will redraw the circuit. I keep this current source and I simply short circuit this voltage source and redraw the other circuit exactly the same way what it is. However, now this I naught is not just I naught. I will represent this I naught as I naught prime, right? Right? This is what superposition is. You first of all disconnect one source, keep the other source, or keep only one source in the circuit. And in the second case, keep only the voltage source and open circuit the current source for the second case. And in that case, you will calculate I naught double prime. In this case, it is I naught prime. And the total I naught is going to be I naught prime plus I naught double prime. So this is just a recall from your DC circuit analysis, how we use the superposition to solve the circuit. So let's solve the first part, which is keeping only the current source. Okay. So when we solve the first part, when we have only the current source, let's draw the equivalent circuit, right? So I will, this is 1 plus J1, this current source. I will keep this branch because I have to find out I naught prime here. And then I will just have another impedance here, which is 1 minus J1 ohms, right? So I have one impedance here, one impedance here. What I can solve is that I can actually solve these two parallel combinations. So this is Z1, let's say, and this is Z2. So I can simply solve these two parallel combinations to make the circuit even more simplified and have only the simplified version here. 2 angle 0. I have one source which I need to keep because I need to find out this current I naught. And then I have an equivalent impedance here, which is nothing but Z1 in parallel to Z2, right? So now simply I can use the current division rule and find out I naught prime, right? I can simply find out I naught prime using current division rule. Using current division rule, find out I naught prime, right? Right, and since Z equals to Z1 parallel to Z2, or you can also write that as 1 plus J times 1 minus J divided by 1 plus J plus 1 plus J. So we can simply solve this one, and this is going to be 1 ohms. So I naught prime, when we divide this one, is going to be 1 angle 0 amperes. So we found only one part of the circuit right now, which is I naught prime. Now, what is the second objective? We need to find out I naught double prime, which means that we need to keep only the voltage source and disconnect the current source. So while disconnecting means I will open circuit the current source in order to find out the second component for this. Okay. All right. So when I disconnected the voltage source, so here was the voltage source, and I disconnected this current source, and I open circuit this one, right? So when I did this one, this is no more. I can make this and this and this in series. When these two are in series, these two are also in series, I can redraw the circuit. I can redraw the circuit again. This is 1 plus J1 ohms. This is the voltage source, 6 angle 0. Now we have one impedance here, and we have another here. So this is, we have to again keep this branch because we have to find out the current in this branch. So this is I naught double prime. This is 1 ohm impedance, and this is 1 minus J1 ohms. Now, how will we find out the current? We can find out the current if we know the voltage at this particular point A, right? In order to find out this voltage, what we can do is that we can simply use a voltage divider rule here and find out the voltage at A point. Right? So this is, let's say I name this one as V1 double prime. So I naught double prime is going to be V1 double prime divided by 1 ohms. So I need to find out V1 double prime. So I can redraw this circuit. 1 plus J1, 6 angle 0. And this is my equivalent. So this equivalent impedance, Z, is nothing but a parallel combination of these two resistors, 1 ohm and 1 minus J, right? So this is a parallel combination of this one. So I can simply write this as 1 inverse. And the voltage across this one is what I need to find out. The voltage is V1 double prime. And I can simply apply a voltage divider rule here and find out V1 double prime as the voltage in the circuit, and voltage divider rule this is this impedance which I just calculated, the equivalent one, this one. After solving this one, divided by 1 plus j, which is this one, plus 1 into 1 minus j divided by 1 plus 1 minus j. Right? So this will come out to be, when we solve v1 prime, this is going to be, oh, so I naught prime is going to be v1 divided by 1, and v1, when I calculate it, is going to be 1 minus j over 4. This is your ampere value. Now finally, what is our goal? We need to find our I naught, so we can simply add I naught prime with I naught double prime to find out I naught. Right? So this is our goal for the superposition. This is the same circuit as the next one, as the previous one, and we can exactly use the same one using source transformation. And in source transformation, what you can do is that you can transform this current source to a voltage source in order to simplify the circuit. Right? All right, so what I do is that I will have a parallel, I will just add up this 1 and j1, and when this voltage, the voltage at this particular point is going to be I times R, which is actually the impedance now, right? So which is simply 2 angle 0 times the impedance, which is 1 plus j. So when I calculate the voltage here, I can convert this current source to a voltage source connected like this one, or sorry, 1 second. Yeah. As so we can redraw this circuit using the voltage source we calculated, and the impedance for this voltage source will come into parallel. This is going to be 2 times 1 plus j volts so this impedance, so this impedance is already in parallel with the current source, so this is going to be in series with the current source. This is 1 ohm, and this is the rule for the source transformation, that we will convert this parallel combination of current source with the impedance to a series combination of a voltage source and the same impedance, right? And now so this impedance will be in series with this voltage source, 6 angle 0, and this is the circuit. We are just redrawing it. This is V2, right? Okay, so what we can do is that we can simply add these two voltage sources. So we have this voltage source, 6 angle 0. Let me make it a little neat. We have this source and we have this source. We can simply add these two voltage sources. We can add these two impedances, and we can simplify the circuit, right? So when we simplify the circuit, we can actually write this one as 6 plus 2 times 1 plus j, and this is the impedance which is 1 plus j, and this is our remaining circuit, right? Yes, this is 1 ohm minus j1. Now we have again a series combination of a voltage source with an impedance. What we can do is now we can convert this one to a current source. We can convert this one to a current source, and we can simply write this one as this equation, as this circuit. So we converted this one. So this was our voltage. This is our this impedances. So we converted this previous circuit, these two, we divided this voltage by this current source by this voltage, 6 plus 2, 1 plus j, 2, this 1 plus j, and make this 1 plus j in parallel to the current source, and this is how it looks like, right? And simply when you solve this one, you can replace this one in this current source. You can simply make these two branches in parallel to each other, right? So when you make these two branches in parallel to each other, you simply can find out I naught using current division law. And you should exactly get the same answer as we got it for the previous method using superposition, because this was the same circuit. So this is how you can basically use different theorems we studied for DC analysis previously for exactly the same way, but using the frequency or complex component path for these circuit elements.